will be recorded. I won't have video feed of myself because, as you can see, there's no webcam here, but I will record my screen. My whiteboard is completely digital. Hopefully we'll see my whiteboard today. Everything will be uploaded on YouTube. All the lecture, everything I write on the board will be saved as a PDF, and I'll post videos on YouTube every day. So if you have to miss class, I'll have all the content for you. I also post all my lecture notes. So let me talk a little bit about myself, and then when we're done, we'll do attendance. One of the goals that I have, and this is going to be very hard, this is the largest cohort I've ever had. This is my 4th year teaching the class, and I think there's 58 of you across 2 sections. It's the largest it's ever been. I think my first year it was 42 or 43, so you guys just keep getting bigger and bigger and bigger. So it's going to be harder and harder for me to remember your names, but I'll do my best, and it usually takes me a couple weeks, but eventually I'll know all your names, and most of you I'll remember your names for the rest of the time you're here. Just got to get my photographic memory to kick in. So let me talk a little bit about my background, why I'm teaching this class. I have a feeling this class has a bit of a reputation in the department. Maybe I do too, I don't know. But this class is intricately connected to me as a person and me as a professional. And I have an interesting story with PChem. When I was your age, so I took PChem 1 in sophomore year of college. I skipped Gen Chem and went into Orgo and decided to do PChem because it's usually a junior's class at my college, and so it was a sophomore class for me. I didn't give 2 shits about PChem. I got B's in the class. I think I got a B- in PChem 1, maybe a B in PChem 2. I showed up occasionally, did the work. Never went to office hours. And my professors, who I know personally still, and I'll explain why in a second, knew me as the kid that really liked organic chemistry and didn't give a crap about PChem. And I wanted to be an organic chemist. So I went to college at Amherst College, just up the street. I'm from Virginia, by the way, so I'm from the middle of nowhere in Virginia. If you guys know James Madison University, that's my hometown school. I went to Amherst College in chemistry. The school was smaller than my high school. There were 400 kids. My graduating class at Amherst, and only 10 of us were chemists. But anyway, I wanted to be an organic chemist. That's all I wanted to do. And I didn't give a crap about PChem. But I went to grad school at UVA, University of Virginia. Just after that, I graduated from Amherst, and I started at UVA just like Memorial Day. Like I had 2 weeks off. And I joined an organometallics group. So we did organic chemistry, but with metal compounds, heavy metals. And I hated it. It was not fun. It was a lot of work, hard work. If anyone's ever done like true organic chemistry, it's a lot of trial and error, a lot of stinky crap, a lot of black tar, a lot of failed reactions, a lot of long nights and weekends. I just didn't find a good work-life balance. I didn't enjoy it. I really liked studying it, but doing it was not fun. So I went to we had like a seminar program for first years in grad school where every professor came and gave a talk about their research. It was in the evenings. And my future PhD advisor gave a talk about spectroscopy. I'll talk a little bit about what I do in a second. And gave some interesting applications, right? That physical chemistry and spectroscopy isn't just physics. You know, as we'll see, it's something that you apply to chemistry. There's lots of applications. We'll have to talk about that today. And I found that really interesting because what you find in PChem is that PChem is a framework that you solve problems with. It's a very, very rigid framework. There's rigorous laws that we use to derive chemical properties. And it gives you a sense of power. You don't have an organic chemistry. In organic chemistry, sometimes you're at the mercy of atmospheric conditions, humidity, water, especially water. But in physical chemistry, if you're looking at fundamental chemical problems and things, you have the power to calculate and predict and to know what you're going to look for, right? You can use a computer, you can use your brain, this rigorous framework that we call physical chemistry to analyze chemical behavior. And I found that really interesting because I couldn't wrest control out of organic chemistry that I wanted. I wanted some control. And so I went to PChem. I became a spectroscopist. I'll talk a little bit about what that means. And I fell in love. And I haven't done organic chemistry in 15 years. I haven't touched it, only PChem. So I had a complete change. And I eventually met my old PChem teachers a couple years later. They do what I do. They're microwave spectroscopists like me. I'll explain what that is. And I told them, hey, I'm in your community now, and they couldn't believe it. And I've been in it ever since. So I graduated 2015 from UVA with my PhD. I went all the way up here to Edmonton, Alberta, home of the Oilers, to do my postdoc. It's the most northern city in all of North America. It's higher than Anchorage. Very, very cold, beautiful place. Spent about 4.5 years there with my wife, freezing our asses off, but we lived right across this bridge right here. There's a beautiful river that bisects the city, and I lived on the south side of the river, and out my window was the beautiful north side of the city. I moved to Argonne National Laboratory in 2019. This is a Department of Energy laboratory. It was originally constructed at the same time as Los Alamos during the Manhattan Project. You know, Los Alamos is where they made the bomb. Oak Ridge here in eastern Tennessee was the other lab that the Department of Energy, that the government developed during the Manhattan Project. That's where they refined and enriched uranium. And Argonne is the lab that they created for Enrico Fermi, famous physicist from Italy, for his discovery of civil nuclear power. So this is where they started to develop civil nuclear power. And the first test reactors, nuclear reactors, were done at Argonne. Nowadays, it's more of a battery place. I did combustion analysis and combustion research at Argonne for 2 years. And then finally, I'm here in the pizza capital of the world. I know there's someone in New Jersey, from New Jersey in here who wants to kill me for saying that, but I love New Haven pizza, and I've been here ever since. So that's my background. Just a little more detail, I'm going to skip this. I've told you this story. About why I'm what kind of physical chemist I am. And we're going to learn today that physical chemistry is a very broad thing. It's not like organic chemistry, it's broader. And in particular, I'm a spectroscopist. What does that mean? Well, I built something called a spectrometer to study the way matter interacts with light. Okay? I'm sure all of you have used spectrometers in your life. I built my own. And use others. And I want to distinguish between these two concepts, because maybe it's not all that clear to you what the difference between a spectrometer and spectroscopy is. You might have heard these two terms, spectroscopy and spectrometry. And I like to distinguish between these two things, because what you've done so far in chemistry is spectrometry. You've done the act of recording and measuring spectra using an instrument that uses light to interact with that matter. Okay? And spectrometry is the act of measuring and the act of interpreting that data. Spectroscopy is the study of how light interacts with matter. It's much more fundamental than that, right? Spectroscopy is the study of light and electromagnetic radiation with chemicals, molecules, or atoms. Spectrometry is the action. Okay? And I'm both of these things, right? They're two different things. And there are people who do spectrometry their entire life, and there are people who don't do spectrometry at all, who are spectroscopists. And there are people like me who do both. Right? I'm passionate about studying the spectra of molecules whose behavior we don't yet understand, but I'm also passionate about building spectrometers to measure those things. The act of measurement in some ways is just as important as understanding the behavior that you're measuring. We're going to focus on those two different concepts throughout the class, the act of measuring versus the theory, right? Application and the fundamentals. All right, what can we learn from spectra? Now, we're not going to talk too much about spectroscopy this semester. That's next semester. But it's important, and everyone does it, and it's kind of the ultimate goal that we want to reach, right? Because spectroscopy, as we'll learn, is the fundamental way that we talk to molecules. We listen to their stories. What can we learn from these spectra? Well, a couple of the things I'm really interested in is what do molecules look like? What are their structures? Of course, you guys have done this before. If you, in organic chemistry, you make a molecule and you put it in the IR, and you figure out what it is. You've done that before. But there are other things you can learn from spectra. You can learn about interactions, right? How do molecules associate, right? Hydrogen bonds, for instance. Not just reactions, right? Not just changing bonds, physical bonds, but how do molecules aggregate together, right? For instance, ask the question to yourself. You have one water molecule, right? And you start to add water molecules around it. When do you get a droplet, right? When do you get a raindrop, right? That's an association question. Maybe we want to think about how molecules change. We call that molecular dynamics, right? How do molecules evolve in time when you perturb them? Maybe you put some energy in them. Maybe they collide with something. Maybe you blow them up with a laser, Right? How does the chemistry evolve in time? You can learn that from spectra. And then we have some kind of more fundamental things, right? Quantum mechanics, right? What can molecules and their spectra teach us about the universe? And this is a very important question. And astronomers think about this all the time. They use molecular spectra to understand how, astronomers use molecular spectra to understand how galaxies form, and how planets form, and how stars are right? The only reason why we understand that stars are the factory of molecules and atoms is because we can measure their spectra, and we know they have these atoms. Right? Hopefully we'll have some time to talk about that. And finally, the thing that's really interesting to spectroscopists is we'll find there's lots of rules in chemistry. I'm sure you've learned that already. The most interesting things in chemistry are things that break the rules. We call these perturbations. How do molecules break the rules? And let me tell you, molecules like to break the rules a lot. It can be really, really small changes. You might not notice it. But molecules love breaking rules. Almost every rule in chemistry is broken. There's only a couple of hard rules in chemistry that are very, if ever, broken. Lots of things break rules. And we'll talk about those things throughout the class. So in particular, I use a type of spectrometer called a microwave spectrometer to study spectra of molecules in my spectroscopy group. Right? I'm a spectroscopist. I think about light and I think about matter, but I use spectrometers to study these things. Key difference. For instance, I just not to denigrate anybody. It's not a criticism at all. But if you think about the spectroscopists in forensic science, people like Professor Kamrath or Professor Marsko, they're not spectroscopists, but they use spectrometers to understand something about forensic science and chemistry and molecular identification. They use it as a tool. Right? That's very powerful. That's why spectrometers are so great. You can use them as a tool in lots of applications. But Dr. Kamrath's interest is not really fundamentally about how molecules interact with what she calls Raman with infrared light. It's more about using it as a tool, an application. Right? So there's a slight difference there. Right? I'm much more fundamental than that. Right? I'm more focused on the art and the creation of, or rather the fundamentals of how light interacts with matter. Okay. So here's some pretty pictures. I study things like this. I've spent a lot of my time studying interactions between molecules. So for instance, these are small water droplets. Literally the smallest droplets of water. Right? How does water associate as you start to make these little droplets? Right? What kind of structures they form? And it turns out that as you start to add waters together, they form really, really discrete and very stationary, if you will, fixed geometric structures. And that's and you can learn a lot about how waters aggregate to themselves and form droplets by analyzing how these structures form. I'm also interested in things that are very big in biochemistry, protein interactions and things like that. How do aromatic rings and hydrogen bonds, how do they compete with each other, right? If you have a hydrogen bond, two oxygens and hydrogens want to interact like water, like they do over here. What if you add some benzene rings to that system? Right? Those benzene rings turn out they're attracted to each other. They want to stack on top of each other, two benzene rings. And what if you have a system that has a mix of these two? Some benzene rings and some hydrogen bonds. Which wins out? So I've spent a lot of years thinking about that competition. And it's a very important problem because one, you see it everywhere. You see these kinds of effects in these competitions and all sorts of complex chemical systems. People don't really understand them very well. In fact, to the point where people make claims that are completely wrong in the literature about these things. Okay? And it's my job as a spectroscopist to decouple these things in an objective way. Unfortunately, the microwave technique is not one that you can just go to the store and buy an instrument like you can in infrared or NMR. You've got to build your own instrument. So this is an instrument I built with some of my colleagues in grad school. This instrument at the time, I think it still is the most sensitive microwave instrument in the world. We're very proud of it. You might see here it says Lamborghini. We called it the Lamborghini. This is an instrument I built in argon. This is a very interesting one. It's a microwave spectrometer, but there's also a laser in there. What we do is we fill this chamber full of molecules, and then we pulse this really, really intense ultraviolet laser in there to blow the molecules apart. All right, so we use a laser as an energy source to start chemistry. And then what we use is we use microwaves, microwave transmitter here, and there's a detector behind this shroud right here. to detect the products, right? So we can do reaction diagnostics, things like that. Okay, so that's all I have to say kind of about chemistry. I just want one more slide about myself, and because I'm a human being, I'd like to talk just one more thing. I'm not just a chemist. This is my 40-hour job. It's more like 50. I have life outside of this. Unlike some of my colleagues, like my handle on the internet has nothing to do with chemistry. I'm not obsessed with chemistry. It's just my job. I'm not really that huge of a science nerd, but I am passionate and I'm committed to my profession. The things I really love, that's too far, are just the things that everyone else likes. Of course, I'm just a normal person. I love Canada. I wish I lived there. Not that I don't like Connecticut, but I'm in love with Canada. My wife is too. I love movies. I've been a movie buff all my life. If someone mentioned something about the CLR, if you're a CLR person this year, you might have heard a trivia that I've seen every movie on the IMDb top 250, and that's just a small subset. I love music. If you're interested in music, come talk to me. I have an archive of reviews. I've listened to something about 4,000 different records in my life. Really, really obsessed. I've played video games my entire life. I like sports, sort of, and I love my Honda. So these are the kind of things that I'm into. I've also been married for 10 years. I haven't added my wife on here. She'd probably kill me for not having her on here. But my wife is in behind all of this, of course. My other hobby academically is writing and lit. I wanted to be an English major and didn't end up majoring in it. I like Japanese literature. This is me. This is my weeb. I'm not an anime weeb. I'm a lit weeb. That's a derogatory term. I apologize, but so I'm not into Yu-Gi-Oh! Or I don't really like anime, but I do love Japanese literature. So post-war Japanese literature after the bomb, really interesting. These topics really inspired me. The idea of the conflicts and the collisions between the West and the East, the fear of the atomic age. If you've ever seen the movie Akira from the 80s, I mean, that's the quintessential existential fear of Japanese post-atomic age paranoia. Japan's a very patriarchal society, very interested in the role of women in art, because women have contributed to Japanese art since antiquity, yet they don't control much of the society, which is somewhat ironic. So I'm interested in these things. And I'm also writing a long-term book project, which is a memoir mixed with my music, journey through music as well. So that's kind of what I do on my side when I'm bored. I'll just talk a little bit about my summer. This is what a scientist does during the summer. All I do is papers. In fact, I have 7 drafts on my desk right now I need to finish. So I didn't really get to have a lot of fun this semester. I did get to go to a bunch of metal shows with my wife. My wife's gotten really into metal this year. So she wants me to take her everywhere. So this year I took my friend for his 40th birthday and her to a band called Misery Signals from Wisconsin. They were on a farewell tour. Went to Brooklyn for that. I took her for my birthday to see Abif, who's an old Norwegian metal artist. And then I took her to see Cannibal Corpse for the first time. So I'm a big metalhead, but mostly just live. I prefer to go to metal shows over any others. Though it's not the only thing I listen to. Here's some shows I'm going to go see. Again, I spend most of my money on concert tickets. I'm seeing Lauren Shore, if you're into metal. I just bought tickets for my friend's 40th birthday for Knocked Loose, Boris, and I love hip hop, so I'm going to go see Juvenile, who's my favorite artist from my teenage years. You guys might not know Juvenile, that's a long time ago. So I'm really excited about that. This summer I went to a conference. Every year I go to a conference, and I also stopped on the way, went to the Air Force Museum, got to sit in an F-16, saw some stuff. I also got to go to the F-117. My dad was in the Air Force, so I got to see planes he worked on there. I also got to go to the Indianapolis Speedway. Never been there. All the years that I've been through Indiana, I've never been. And I got to go visit, actually this is the home place of my technique. So the original kind of modern microwave spectrometer was built at the University of Illinois. In this building right here, they have a nice little sign. So that's kind of my home base, if you will. My romantic home. Okay, so that's all I have to say about myself. 2 things that I want to tell you about me that's important to you. One, I'm somewhat hard of hearing, partially because of unprotected metal shows for 25 years. I've not been responsible. So I have kind of poor hearing. So just yell. I will never be offended if you interrupt me. In fact, I encourage you to say, Seifert, please stop. Okay? If you have a laser pointer, you can even bring a laser pointer and point at the screen if you have questions. Right? Please, because that's the first thing. The other thing is I'm Asperger's as hell, as you've probably already figured out. I have a hard time sometimes making eye contact. So if you have your hand raised and I don't see it, just yell for me. It helps me and it'll help you. I'll never be offended if you interrupt me. Okay, so let's talk about the class. Where are we at? Okay. So before we jump in, I'm just going to kind of summarize the syllabus. All right, I'm not going to go through the syllabus. This is just kind of summarizing the slides here. You're welcome to look at it. I want to talk about my philosophy in this course, and then at the end of this, when we have time, we'll talk about what PChem really is. All right. So this is my philosophy about this class. But the first thing is that PChem, when people think about physical chemistry, they think physics plus chem. And there's something to be said about that. And in fact, I'll show you, I'll have a reading for you for Wednesday that talks about this idea, about how physical chemistry, let's say how physics is intertwined with chemistry. And physical chemistry, you would think, is the way that we disentangle those connections and understand the connection between physics and chemistry. That's fair. But I don't really like to think of it that way, because I'm not a physicist. I'm not very good at physics, but I'm a good physical chemist. And the way that you should think about PChem is to use the Latin term for PChem, which is chemiae ab initio, which is, idiomatically, chemistry from first principles. Right? Ab initio means from the beginning in Latin. Right? So the idea is chemistry from the beginning. We make no assumptions. We will make some, but we'll make a minimum number of assumptions and see how chemistry falls into place from there. Right, so from first principles, right? We're not going to make any assumptions. What can we learn about chemistry from the basics? More practically, the only people who fail this course are the people who don't turn in their work. Simple as that. Everyone, if you choose not to engage with the course, I'm not going to give you a grade. But if you turn in your work, you show the class, you make some attempts, you give me a good faith effort, you'll pass the class. Guaranteed. Don't be scared. Right? The only people who have ever failed this class are people who don't turn in their work. This class in particular is not a weed out class. I think I say that next one. I want you to, and it's not a class for you to become a master at PChem. I don't expect any of you to become a master at this class. I certainly wasn't. I'd say I had maybe 40% mastery after my first 2 semesters at PChem. Right? But I want this to be an invitation for you to consider the PChem point of view. Right? And to engage with this kind of philosophy that we have about constructing chemistry from the bare bones. Right? And to engage with this idea of building it from the foundations, to understand the underlying theory and the underlying logic of chemistry. Right? So I'm not here to make you guys P-chemists. Don't expect you to be P-chemists. I expect you guys to be forensic scientists and chem engineers and probably other types of chemists. Maybe 1 or 2 of you will be really into this, and that's great. But what I want you to do is just be an invitation. All right? I'm not forcing you to become me. All right? I'm not building you guys into me, but rather I want you to start to think about chemistry the way that a P-chemist does. Okay. This is the biggest thing about this class, and I'm going to drive this point home multiple times. I'm a cracked open door policy. Right? Now, my door's not always open, right? Because I have other responsibilities. But if I don't, my door's open. All right? You're not alone in this class. It's a hard class. Every single person who come out of here, whether you got an A or a D, will tell you it's a hard class. But you're not alone. Because, one, there's me. My office hours have always been, for years, very, very effective, and I'll prove this to you in a minute. But we also have Kayla here. Where's Kayla? Kayla's way back in the corner. Thank you. Kayla's your LA for the CLR, and you'll get to know her better. She'll set up her hours with you. Kayla will also be your go-to. There's another student, a graduate student named Joy, who does the other section. She'll also be doing things in joint sessions. My LAs usually have the highest ratings in the entire school, and that's because I like to build communities of help. This is not a class where you're going to be alone. All right? I'm not going to expect you to build community and study groups, but I'll allow you to. All right? And I encourage you. Also, you're welcome to come talk to me. Cracked open door. Right. my fundamental philosophy with students, and you'll see this in my policies, is that what you choose to give to me in this course, I will return in kind to you. Right? If you want to come into this class, sit in the back, take your notes, go home, just do the bare minimum, don't really communicate with me, that's fine. No problem. I'm happy to give you a grade. I'll give you a good grade if you do well. Right? But if you're kind of the student who likes to build relationships, needs some help, maybe needs a little hand-holding, or maybe you just like to talk, maybe you're really interested in the material, if you come to me and you make effort and you show me you make effort, I'll make effort to you as well. All right? It's a two-way street. Right? But I can't help everybody, but not everyone needs help. So it's up to you. Right? But I promise you, if you make the effort, I'll make the effort back to you. And finally, this is, you guys are all seniors mostly, so this is kind of irrelevant. I assume mutual trust, respect, and empathy in this class. What I mean by trust is I'm assuming no one in this class is ever going to cheat. All right? I'm not expecting that you will, or that there's going to, I'm not always worried, I'm never worried about it. I'm under the 100% assumption that this class is 100% honorable, and if you disappoint me, then I'll make it very clear to you that you disappoint me. That's never happened before. So I'm not scared about you cheating, I'm not scared about collaboration. In fact, I encourage it. All right, but just treat each other fairly and with respect in me as well, and I will to you. Okay, so that's enough of that. Let's talk about the fundamental parts of the class. The assignments, there's 10, talk a little bit about the grading, kind of weird. 10 total assessment equivalents in this class. What do I mean by that? What it means is that everything kind of has a base weight, okay? There's a class survey that's posted, doesn't get a grade. I'll talk about it in a second. But you do, if you turn it in on time, you'll get a free unexcused late submission on the homework. There are about 5 or 6 problem sets. There's usually about 2-week turnaround, 10-day. They're always due on Friday at midnight. And then I kind of have an open submission policy until the Monday after. Okay, so you kind of have to turn it on the weekend. They're fully collaborative. You can talk to anybody you want in the class. Make friends with people next to you. If you have friends in the class, work with them. Work with Kayla, work with me. If you have an alumni who's really good at it, you can work with them. Totally okay with that. I want you to build communities. I think that's a good way to learn. There will be 2 take-home open book exams. One will be issued kind of around the beginning of October. And there will be one that'll be a final that I'll issue on the last day of class, and it'll be due at the end of the exams. So on average, about 7 to 8, 10-day turnaround. The only difference is no collaboration. All right? I'm going to cut off office hours, cut off CLR hours. I'm going to, again, assume you guys aren't going to collaborate with each other. But basically, they're like the problem sets, a little shorter than the problem sets, and there's no collaboration. All of the assessment equivalents are all graded on a 3-point scale. Right? I'll explain why that is. There's no A's, B's, and C's. You'll never see those on your exams or your problem sets. You'll get a 1, 2, or 3. And they basically they're about expectations. Right? So I have kind of a qualitative idea of what kind of expectations I get. And that's kind of ambiguous to you. That's okay. As you'll see, it's somewhat holistic. So basically, your homework and each equivalent will be graded 1, 2, or 3. All right. Most people will get 2s. Right. So anything between like a B and like a C minus, B plus to a C minus gets a 2. Okay. A work gets 3, and then below expectations is like you didn't complete it. Basically, it's incomplete. That's what that means. Or you have significant problems, significant issues with your work. All right. So there's some correctness in your work that's important here. Precision, we'll talk about what that means later, organization, and just your thought. Because there will be qualitative questions, thinking questions, and I'm looking for intelligence in those. So what you should think of these as not so hard like a regular chemistry class, but more like an upper level humanities course. Okay? Think about the grading in that way. The way that the grades are accumulated is through a labor-based contract grading system. Right? Your final grade is determined by how much work you complete and how good is it based on the benchmark. Okay? So let's say you turn in all your work, it's all kind of B minus, it's good, there's a few small problems, but you do all the work, you turn it in on time, everything's great. You'll never get anything less than a B in this class. Simple as that. Basically, if you're just here just to hang out, you'll get a B as long as you do your work. Right? If you do better on the work, right? If you're an A student, you work hard, and you're improving, you'll get better grades. You won't ever get worse grades. And that's because the expectations are dynamic, right? They're not the same for everybody. Of course, this is a quantitative class. There are right and wrong answers to things. But if, for instance, I look at organization and thought process and critical thinking, if you start, in the beginning, you kind of have rough homework, kind of sloppily done, most of it's correct, you'll get a 2, and then you come back to the second problem set that I give you after all the feedback in the first one, and it's way better, I'll give you a 3. But imagine I had people in last semester who did this, who were 3 students. They were doing really good work, and then like halfway through the semester, they kind of slacked off, probably because they got senioritis. And I started giving them 1s, even though it was kind of 2 work, right? Because I want to motivate you to do better. Okay? So what that means is, and this is kind of complicated, this all comes together. Basically, you can determine what your grade is based on your things that you return. Okay? There's no calculations to be done. Again, if you do everything within meets assessment, and I'll talk about the cutoffs in just a second, you'll get a B. Right? If you do better than that, you'll do better. If you do a little worse than that, you'll do a little worse. What these cutoffs mean is that, for instance, let's say, for instance, you've been late on 5 of the 6 homeworks. That means that the best grade you'll get is a D. Okay? Regardless of how good the work is. However, let's say, for instance, now we see here the assessments for the assignment says that a D is 3 meets, 3 2s out of 3s, and 4s 1 out of 3s. Okay, so the things you turn in are kind of between a 1 and a 2. Now imagine you got this kind of distribution where you have, say, like 4 and 6, right? You have 4 2s and 6 1s, but you've turned everything in on time, right? That'll put you, it turns out, puts you somewhere in the C. The idea, what turns out the way this works, is that if you turn in all your work, all right, you turn it in on a reasonable time, regardless of the grade, all right, assuming it's complete, and you turn it on time, the lowest grade you'll get in this class is a C. So C minus, D, and F are reserved only for people who don't turn in their work. Simple as that. I had a student last semester who worked really hard, spent a lot of time, very organized work, very meticulous, very, very good homework. All the answers were wrong. Did all the problems wrong. Got a C in the class. Because I'm looking for effort. I'm looking for you to think. Right? If you're struggling with the math, that's okay. Right? I'm not going to fail you because you're struggling with math. And that was the issue, was just on the quantitative skills were not up to par. But the thought process was there. The effort was there. The engagement was there. Always came to class, worked hard, turned things on in time. They came home with a C. Okay? The only people who have ever gotten F's in this class are people who don't turn their work in. Any questions about that? Well, that's a big one. All right, so if you have questions about the grading in the future, just ask them. All right, so just some tips. Again, attend class. It's really easy to fall behind in this class because there's a lot of material. I don't grade attendance, by the way. I will note it in a second, but I don't grade it. Textbook is not required. I'll talk about that in a second. Expect to read, expect to think. There's probably more thinking that you're used to in a chemistry class. And some of the questions are a bit like puzzles. If you like solving puzzles and solving mysteries and things like that, this is a good class for you. Because it will require a little out-of-the-box thinking at the time. Right? Some critical thinking. It's not really just let's take the equations, memorize them, and apply them. You've got to have a little more thought than that. Ask questions. As I said, interrupt me. Please ask questions. Any questions valid. If you have it, someone else does. And as I say, build on learning. Right? You can work by yourself. I don't care. Totally fine. But if you like working with other people, please do. You come work with Paola. You come work with me. Come work with each other. Please do. I encourage it, except on the exams. And I'll back these up. Right? I went back through all of my student evaluations for the last 2 years. And they ask you that question. What advice would you give to another student? And they never tell you what the answers to these are, but I will. They fall into 3 very simple classes. One is come to office hours. I lost the the drama of this. Go to office hours. Go to office hours. Go to the LA. Don't be afraid to email Dr. Seifert. Go to office hours. Definitely go to office hours. Always go to office hours. Go to the TAs, and Seifert's office hours should be a priority. Right? Come to our hours. I'm not going to bite you. Certainly Kayla will not bite your head off, and I won't either. Bring your effort. Effort matters. It is a complex class, but I'll walk you through it. Take good notes and listen to lecture. Of course, it's difficult, but you'll do fine if you take notes and turn in assignments. Right? I love the grading system. It's a hard class, but if you meet with Professor Seifert, you'll do just fine. All right? Come see me if you have a problem. I'll explain the problem to you. No one ever comes out of my office hours understanding less than when they came in. All right? And then the other one, which is a little more negative, but it's okay if PChem's not for you. These are assessments from students that I think, 100% because they're anonymous, who passed the class. And I'm going to read this one to you. And this is 100% correct, and so, but it's okay. I'm not a perfect person. I'll just read it to you. As much as I enjoy Dr. Seifert, I strongly dislike PChem as a topic. Almost none of it makes sense to me. At this point, I don't think I could tell you anything about PChem other than that there is a particle in the box, which is the topic for next semester. Doing the lab in junction with the class has definitely helped me understand the topics. We'll talk about the lab in a second. I go to LA office hours weekly on homework assignments, do well on them, take-home test, but the take-home test seems unrelated to anything we've done in the homework assignment. I disagree with that. I felt like I was going to the midterm blind. Anyway, this was like 3 years ago, right? So, and both of these are just people who just it wasn't a good fit, all right? It's not going to be a good fit for everybody in here, and that's okay. But both of these people passed. All right, I'll make sure you get through it. Okay, so the final slide I have here before just a few other things is the schedule. So this may change a little bit. And this is Tuesday, Thursday, but it's the same idea. The idea, we're going to talk about a lot of math at the beginning. We'll do conservation laws, units, dimensional analysis kind of stuff at the beginning, statistics, multivariable calculus. And the reason, I'm going to focus more on these than I did before. And the reason why, you might not be aware of this, but I think starting this year, the incoming forensic science students that are chemistry will not have to take Calc 3 anymore. This class needs Calc 3, because we tell you, we do things in 3 dimensions. You need triple integrals. You need multivariable calculus. We do things in 3D. So I'm going to try to reconstruct the beginning of the class a little bit to integrate more math skills. Okay, so we're going to do a little more calculus, and we're going to assume less of you in terms of mathematics for the first month. All right, we're going to spend more time on the math, and we'll use the topics of the class, the introductory topic of the class, to motivate those mathematics examples. Okay, I'm trying to adjust the class so that this becomes more of an integrated mathematics class eventually, without taking away too much chemistry. All right, once we do that, we're going to go into the laws of thermodynamics. We're going to do thermo, classic thermo. This may be condensed a little bit, but I think we're pretty much there. We'll talk about enthalpy, Gibbs free energy, entropy, very interesting topics. And then the first take home will be kind of these things, right? They basically be a little basic multivariable calculus, some statistics, and some thermo. And then the second half of the class, if you will be mostly focused on these 3 topics, basically on phases and mixtures. Phase transitions are a very, very interesting topic. I'm very interested in them. I'll give you a very different approach to think about phase transitions than you've ever had in your life. All right, so we'll look at a new way to think about phases. We'll talk about mixtures. We'll introduce an idea of what's called the chemical potential, which will allow us to do equilibrium. Right? We're going to learn about what equilibrium is from the ground up. All right, we'll spend some time in that, and then we'll move into kinetics, which I think is really the interesting part of this class. Right? What happens when you collide 2 molecules together? Right? We'll talk about that. How do we measure things with that? And then if we have some time at the end, we'll talk about some advanced things, depending on how much time we have, and then we'll have a final exam that'll be issued on the last day of class. Okay. All right, so that's all I have for this. Just any questions about the schedule or anything? I'm going to do attendance really quickly. How much time do we have left? 30 minutes, great. This is the textbook. McQuarrie and Simon's Physical Chemistry and Molecular Approach. The paperback version new is, I think, is $70 on Amazon. This is hardback cover. I think retail is $130, but you can get it used for $50. It will cover both semesters. Okay? So if you're a textbook person, I highly recommend buying this. It's a really good textbook. It's dense as hell, and it's worth the money. There's really good math chapters, really good descriptive and historical explanations of physics, chemistry, and it goes through a lot of things that I can't go into detail. So I recommend, if you like textbooks, to get this one. I've had this one this is the book I learned Pekin out of. So I've had this book since 2007. All right, it's a great book. There are also smaller versions of this as well. I'll send a link out, but if you're only here for one semester, you want a textbook, there is a condensed version of this split into 2 volumes. There's one for thermo, which is the first semester, and one for quantum, which is the second semester. So you could save a little money if you want to buy it separately. And I'll post a link for those as well. Okay, so let me just really quickly move the canvas. And I just, what I want to do actually, I'm not moving the canvas. I take that back. So let me hold this up. I want to do attendance now. So let me get everyone's name. I'd like to know what you like to go by. If you have a pronoun preference or a nickname, or you just want to correct your pronunciation, that would be fine. So we have, I don't know where this J is. We have Brian Bajor.
Yeah.
Bayor? How's that J go? Badger?
Major.
Bajer.
Major.
Like major?
Yeah.
Okay, thank you. All right. Ian Bielka? Ian?
Ian Bielke.
Bielke, thank you. I'm sorry. Long E. Jack Celebruno? Jack. Ashlyn Chavez? Hi, Ashlyn. Some names I recognize. I saw Josh in the back. Hi, Josh. I saw G as well. G is over there. Hi. Caitlin Zifra?
Hello.
How do I get your last name?
Zifra.
Zifra. Okay, the C is silent.
Yeah.
Easy. Isabel Darris? No. Joseph DiGiacomo? Did I get that right?
No, that's not
No, tell me, what is it?
It's DiGiacomo.
Oh, man, I really screwed that up. Oh, okay, I got you. I see where that is. I got to speak like an Italian. I apologize. Riley Downs.
Right here.
Hi, Riley. Noelle Freeberg. Hi, Noelle. Congratulations again. Claudia Gross. Claudia. Bridget Gudzak. Did I get that right?
It's Goodzak.
Goodzak. Mark Harvin? Is it Harvan or Harvin?
Harvan.
Harvan. All right, you got it. Harvan as in minivan. Got it. Kalia Sue? All right. Kaylee. Kalia.
Kalea.
Kalia.
Kalea.
Kalea. There we go. The A. Yeah, I'm sorry. Thank you. Megan Jenkins. Hi, Megan. Met Monica. Michael Kane. Michael. Kaya Kinsulak. Did I get that right?
Yeah, actually.
All right, excellent. Elizabeth Leggieri?
Legere.
Leggieri.
Yeah, you can call me Lizzie.
Lizzie, thank you. I met Charlie Matheny.
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 Yeah. You think of there's a person in a band, and then there's also the baseball player.
I think Mr. McFeeny from Boy Meets World. That might be a little old for you guys.
I understand that one too.
Okay. Sydney's not here today. Carol Silva?
Yeah.
Carol? Yeah. Do we have 2 Silvas in here? Josephine Pizarros?
You can
Yes.
call me Josie.
Josie? Jamie Pereira?
Here.
Hi. Molly Raffy? Hi, Molly. Emily Rivera? This one's, I think I got this. This is Kirill Semyolin. How do you do your last name? Semyolin. All right. That one's much easier than I tried. It's Kirill, yeah?
Mm-hmm.
Macy Smith?
Here.
Macy. Madeline Smith?
Here.
In front. Kylie? Swoop?
Here.
Hi, Kylie. I saw Rebecca, didn't I? Is she hiding in the back? Way in the back. Hi. Welcome back. Jordan Zeisa? Zeese. And Megan Zagato. All right, excellent. Everyone's here. Thank you. So I'm going to do that for like the first 2 weeks. Hopefully I'll remember everyone's name. The more you come talk to me, the easier it will be for me. Okay. What do I have left to talk about before the end of class? Let's just jump in. Let's just jump in. I want to talk just very, very briefly about PChem. All right, and this is not something you really have to take notes on. I just kind of want to set the stage for you a little bit. All right, and I have an article for you. In fact, let me just show you on Canvas right now. In general, I do a lot of stuff on Canvas. You'll probably already notice that I did my announcements on Canvas. I post everything on Canvas. Basically, if you need information, it's on there. You can always email me. I respond to emails usually until about 11 o'clock at night. And my average turnaround time is about 10 minutes. So just email me if you have a question. Under Module 1, there's a reading here, More is Different by Philip Anderson. It's a brief article from Science from 1972. Phil Anderson is a physicist. He studies what we would call condensed matter physics, solids and fluids and magnets and things like that. He's a physicist, but it's a really, really, really interesting philosophical discussion about the hierarchy of science. And I think it's a really, really good perspective on this class. Because what I want to do is I want to get you out of this idea that somehow PChem is physics plus chem. I mean, it kind of is. But it's a very simplistic way to look at it. What we should instead look at is how does physical chemistry tie into physical science in general? And there's a sense of hierarchy, right? Maybe you can think about this. How do you, for instance, organize the sciences in terms of whatever metric you want to use? Complexity, the assumptions that you make, abstraction. How do you want to organize the sciences together? Right? How do each of the sciences influence each other? Right? And if you ask most people, and this is a perfectly reasonable way to look at things, is if you think about the hierarchy of science, where does chemistry lie in all of the sciences, right? Most people would say it looks something like this, right? We'll call this like there's a different term for this, but we'll call this the hierarchy of science. And I'm going to put this in quotation marks because we're going to talk about why this is a bad way to look at things. Right, but the way that most people would, and if you ever follow XKCD, for instance, the comic book or the webcomic, Randall Munro has a kind of same idea. I don't really agree with it, but let's talk about it. Well, what is the most pure science of them all when you think about it this way? What is everything pulled from? And of course, what you think of really is mathematics. Right, the top of the food chain, if you will, of intellectual science is math. Right? Math, we pull truth out of nothing. Right? Math is very, very rigorous. There's a set of assumptions called axioms, and you drive everything from them. Makes no assumptions other than these things that we assume to be true. Right? Math is the most fundamental science of them all. Right? But we don't learn, just math by itself, we don't learn a lot about the universe. I mean, you certainly can, right? But what do? Well, we come up with mathematical theories that predict things about the physical world, and we go test them, right? And what do you get when you do that? Well, you get physics. Right? So you can think of this as like applied, right? By application of math to the physical world, you get physics. Okay, that makes a lot of sense, right? And when you learn physics, especially fundamental physics, it's a lot of math, right? We build things from mathematical models to understand physics, right? And so let's go to the next thing, right? What happens when you apply physics? You start to put a bunch of moving bodies together that are all attracted by physical forces, and what do you get? Well, you get chemistry, right? Keep going, you have chemistry, right? Applied physics in some ways, of course there's other ways to think about it, but in general you can think, okay, well, chemistry is just applied physics. Right? So, and then what is applied chemistry? Well, we would call that biology, right? Right? We can just keep going down this list. What is applied biology? Maybe physiology, right? The study of the body. Interestingly, historically, other than math, the way that chemistry was developed actually went this way. The original chemists were physiologists. It didn't come from math, right? The original chemists were not mathematicians, they were physiologists. So in fact, it's interesting, historically it's the other way around. But you can keep doing that, right? And what's applied physiology? Well, there's different types of applied physiology, but maybe one is psychology. Right? I think most people would agree, kind of naively, that psychology is somehow a subset of human physiology, right? It's the study of the consequences of our sentience, right? Which is a part of our physiology, right? And so this is a totally reasonable way to think about things, right? That these things all connect this way. Right? And where would physical chemistry fall into this? Well, it's very easy, right? Physical chemistry would fall right here, right? It's this process. You would think physical chemistry is this connective linkage between physics and chemistry. Right? It goes right here. Right? And of course, this arrow right here would be biochemistry. Right? This is mathematical physics. That's just the term for it. Right? I don't know what you call biology or physiology. Medicine. This would be medicine, right? I'll just write that. Right? This is like medicine. Chemistry and biology is biochem. Physiology is psychology is psychiatry. Right. You have these subfields that are kind of like the little connective tissues between all of the major fields of science, right? And so, but here's the problem with this design. What does this assume? Let's think about it in terms of majors, kids that take these classes. Right? How do you often associate? Well, this is all stereotyping, but let's take my guess here, right? How do we organize and characterize the intelligence of students, kind of in a jovial, naive way, based on these, right? We often think of psychology as the BS major, and we think of math as the hardcore one that only the crazy nerds take, right? And there's some truth to this because math is hard. And psychology, because it's very abstract, right? You have to have a certain type of mindset to understand math. But psychology is easier to get to because you yourself are a human. You experience your own psychology. You're an expert in it, right? Because you experience it every day. Right? It doesn't mean there's not a sense of validity here. But one of the things that you can extrapolate from this hierarchical sense is that there's a level of increasing abstraction as you go down, right? Math is the purest. Physics is, we're going to assume that everything are little spheres and spherical cows and there's no friction, right? We're going to make some small assumptions, but we're going to abstract away some of the complexities of math. One of the classic examples of where we simplify the mathematics in physics is we assume there's 3 dimensions, or 4 dimensions if you do relativity, right? We don't worry about things in 10 dimensions or 100 dimensions or infinite dimensions, sometimes, because the world is 3-dimensional. So why do we have to worry about the other ones? Right? So we're adding these levels of abstraction. Right? The abstraction from physics to chemistry really is, as we'll learn, is energy. Right? Chemistry in some ways is low energy physics. Physics at the bottom of the energy scale. Right? And then biology, if you think, is kind of like chemistry aggregating in such a way that it becomes a biology. Right? You've abstracted some of the fundamental nature away and kind of smeared over it to build up new behavior and to simplify. Right? So you would think that naively what you're doing here is you're simplifying as you go. Simplifying your understanding of the fundamental laws of nature. But everyone knows that this is completely and utterly wrong. Let me give you an example of that, right? Let's just sit here at physiology and psychiatry, or psychology, right? Right? I'm a clinically depressed person. Been taking antidepressants for 25 years of my life, and I'm not afraid to admit it. Well, that's a question of physiology. That medicine, the antidepressants, help me feel better. They make my psychology stable. So I say, hey, right, I can solve my psychological problems by coming up with a physiology solution or a biology or chemical solution, right? Right? By using selective serotonin reuptake inhibitors, SSRIs like Prozac, right? Or something like that. Right? So I'm using the knowledge that I've gained from those, the more advanced knowledge, to be able to manipulate something simpler. But that's not true, because I can dose myself with lithium and everything in the world, and I'm still a total, complete, useless human being that can't interact with anybody, because there is behavior that's emergent in psychology. I have behavior. My biology influences my behavior, but it doesn't help me necessarily control my behavior, because some behavior is reflexive, right? The way I interact with stress and stimuli is a reflective thing. And what do we do to break ourselves of those bad reflexive habits? We go to a therapist, right? We go to a therapist. We do DBT. We do psychotherapy, right? And that's always done in a combination with medication, because you need both of them, right? And the idea is that you're not actually abstracting, simplifying as you go down there, because every time you go a level, new emergent complex behavior appears, right? Physiology doesn't really tell you anything about the psychology, right? Psychology in some ways is an emergent property of our physiology. Right? Nothing in what we understand about physiology, other than we know we have a complex brain, explains why we have such complex psychology. In some ways it's emergent, right? And you see this at every single one of these. You would think chemistry is simpler than physics, but there are emergent behaviors in chemistry that you really can't understand in physics. And this is what Anderson's article talks about, is this connection right here, and also in biology, that even though you think you're abstracting, there is new complex behavior that appears at each level that's more complex than it was before. And that's especially true in physics. Because when you think about the physics of the Large Hadron Collider, high energy physics, big collisions that they do in those big particle accelerators cost billions of dollars, you think, well, that must be really, really complex. Right? Think about the physics you have to do to figure that out. And it is true, it is complex. But if you look at the mathematics of that theory, it's actually really, really simple. It's actually simpler and more restrictive than anything in chemistry. And all of the rules and laws of chemistry are more restrictive and simpler and more elegant than biology. Things get more complex as you go down. Right? It's not really that things get simple. The way that we interpret things and the way we study them and do research, what we call this reductionist pathway, right? That we're reducing the complexity. But in fact, these fields become more complex as you get higher and higher and higher down the chain, lower in the chain. Physics and math in some ways are incredibly rigid and very straightforward. They're hard, don't get me wrong, but there's some rigidity to them. They don't flex. But every time you add, there's more and more and more flex. And every time you add more flex to you add more possibility of exceptions, the more complex things. Okay? So psychologists and physiologists as a science, very, very hard, very complex, and that's why they're poorly understood, right? But you can go, if you study physics for the last 100 years, we're basically done with physics. We pretty much understand everything about physics except for kind of things on the edges. Physics is more or less done, despite the fact that you would think it's the hardest of all of them. It's the one we know the best about. So this is a bad way to look at things. I think in some ways it's almost derogatory towards the sciences because it gives you the wrong perspective. So the way I want you to look at this class instead, I'm going to kind of close this off. All right? So my view is to think about this as a circle instead. And I'm going to focus just on physics, chemistry, and biology, which are the things that are really relevant to chemistry. Right? So instead what we'll do is we'll put chemistry here. Our little world of chemistry. Inside of there is organic, analytical, you name it, inorganics, anything chemistry related. There's another world called physics in here. And inside of there is subatomic physics, nuclear physics, condensed matter physics, quantum physics, high energy, you name it, right? There's all sorts of physics, right? And then there's also this world over here that's biology, right? And we know what biology is. That's genetics, and living beings, and and so on and so forth. And there's an interconnection between all of them. It's a graph that everything is connected. There's exchange of information and ideas between all of them. Right? And the question, of course, is how does each of these influence each other independently? And of course, there's some overlap here. Right? So how does, for instance, chemistry influence physics, or vice versa? Well, those are pretty obvious, right? What are some things that we've used physics for to help us in chemistry? Right? What are ways that physics has been applied to help chemistry? Right? I'm just thinking practically, right? What about the laser? Right? We use lasers in chemistry all the time. Right? Spectroscopy. All the first spectroscopists in the world, all the people who created spectroscopy were physicists. It's a physics thing, and they realized that they can apply it to chemistry. Right? And there's other types. Solid state, right? Materials. Any sort of materials chemist is very interested in physics. How we understand magnetism and magnetic materials depends on physics, right? Physics has brought so much to chemistry. Of course, it's more fundamental than that. I'm just thinking of applications. Right? Chemistry and physics interchange these ideas a lot. Chemists use these tools, physicists use these tools. There are different types of things that physicists are really good at that we're not so good at, and we learn from them, and not so much vice versa, but physicists aren't so much interested in molecules, but they have techniques, and they have ideas that help us understand chemistry, right? Exotic materials, magnetic materials, so on and so forth. Right? And what about physics and biology? Well, if you're in the seminar class, chemistry seminar, you'll learn a little bit about this semester, the thing called soft matter physics. For instance, the aggregation of bacterial cultures, aggregation of what are called biofilms, for instance. That's a physics problem. How do bacteria colonies physically form and geometrically grow in a certain media? Right? That's a good way to think of that. The thing, I bet you every single one of you has used a physicist's application in a biological setting in your life. You might not know it, but if you've ever been to the dentist, you have, right? Imaging, MRI, CAT scans, X-rays. If you didn't have physics, you wouldn't have that in biology, right? Everything we know about our insight in a modern world requires not only physics, but quantum physics. Nuclear magnetic resonance, MRI, CAT scans, PET scans, right? Positron emission tomography. The positron emission tomography, that just sounds like a physics term, right? But it's something that we use for imaging all the time. Chemotherapy, right? Radiation treatment, right? That's all stuff created by physicists, applied for biology. Right? You do physics all the time in biology. And of course, for chemistry and biology, we all know this, right? Those are proteins and genetics and separations, right? Electrophoresis. You can think of all sorts of stuff, right? There's so much connection between chemistry and biology, right? And so there's this interchange of information between all of these, and all of them use all of them, right? There are biologists that use lasers and spectrometers. There are physicists that study proteins. Electrophoresis is a technique created by physicists. And of course, we all use imaging. We always image. We use MRIs, we use NMRs, we use IRs, we use UV-Vis. Right? These are all techniques generated and created by physicists, and using the physics, the laws of physics, to create imaging techniques. Okay, so where does physical chemistry fall into this? Right? As I said, in our kind of reductionist approach, physical chemistry falls right in between chemistry and physics. It's the application of physics to chemistry. There's nothing wrong with that, but it really serves to miss the point, because physical chemistry is important here too. And it's also important here, it turns out. There's a connection between all three. And so my argument is that all of these techniques, lasers, materials, understanding of materials and exotic materials, magnetism, emergent properties, superconductors, LEDs, that's a good one. LEDs is a good example of using chemistry and physics together to make light. Imaging, soft matter physics, protein genetics, biophysics. We all use these things together. And my claim is that what physical chemistry is not this connective tissue between physics and chemistry, but rather there is inside of this circle, let me do it slightly differently. There is a triangle of connective tissue between all of them that we call physical chemistry. All right? This is from the point of view of a chemist. Now, a physicist might look at this and say, that's not physical chemistry, that's physics we're doing. Right? And a biologist will say, I don't even know what physical chemistry is. Right? But from my point of view, when I'm sitting here looking out, I see the interconnections between these three, right? The framework that we do, the measurements, the way that we tackle problems, the way that we do predictions, the types of techniques that we use, right? How do we measure things? How do we quantify things? These are physical chemistry questions. All right, so physical chemistry is this connective physical tissue between the hard sciences from the point of view of us. Again, there's a different point of view from the other corners of this, but from my point of view, physical chemistry is what binds everything together. And the idea is that physical chemistry is, let me just write this down. Just put it down here at the bottom. So PChem is a framework for, I would say, two different primary goals. One is prediction. Right? First is prediction. We put two things together in a Erlenmeyer flask at 100 C. What happens? Right? Well, you might have some idea from organic chemistry what might happen empirically, right? But what if you want to predict it? Right? What if you really want to know what's going to happen to certainty? Right? You've got to do some sort of prediction. You have to have some sort of theoretical framework to analyze that question. That's what PChem is. PChem is that framework for prediction. It gives us a set of tools and a way to understand the universe that allows us to calculate things. There's a phrase I like to use, which is shut up and calculate. Sometimes in PChem, you just shut up and calculate. And that's because PChem allows us to do that. Right? PChem says that there is a way, for given A and B in my flask, to know what happens after a day or some amount of time of months. Right? I can predict what's going to happen. And I can predict things to, hopefully, arbitrary precision. I can give you kind of hand-wavy A and B might convert to C, but maybe you want to know how fast it'll convert to C. What's the percent conversion? What if it doesn't work at all? Why? Well, those are questions PChemists answer. So what we're interested in is not only prediction, but and this is kind of more of a holistic way of looking at it, is the questions we answer in chemistry is why and how. Why does something happen and how does it happen? We'll answer those questions this semester as best we can. Of course, it's a rabbit hole like all sciences. It goes deep. The questions that we don't ask in here is not what. I'm not interested in creating things. I'm not interested necessarily in answering what is chemistry or what is a certain chemical, but why does chemistry happen and how does it happen? Those are PChem questions. Answering why and how. Mechanism is important to us. In fact, mechanism is the entire, when you think about organic chemistry, the only thing we care about are mechanisms and kinetics. How fast does something happen and why and how does it happen? That's what we care about. And finally, kind of a more experimental point of view, it's also a framework. I'm just going to kind of cream in here at the edge. Measurement. This is the experimental side of things. We can make a theory to predict something to happen. Right? We've predicted using our prediction, using our theory. We have a hypothesis for why or how something happens. Now we have to prove it. So what do? We have to measure it somehow experimentally. right? And the concept of measurement is central to P-Chem. Say something like 70% of P-chemists in the world, maybe even 80%, are focused primarily on this question, measurement. Because this can be kind of hard. Often we go to people who are smarter than us and say, hey, can you help us predict this? Right? There are people who study the prediction, we'll talk about that next class, a lot. And they only do prediction. We call them theorists or computational chemists. They do prediction. But a lot of us are measurement people. We measure stuff. We want to solve a chemical problem. We don't know how X turns into Y. Why does it happen? How does it happen? Well, you got to build an instrument to do it. Not only do you have to build an instrument to do it, you also have to analyze the data it gives you. You also have to find a way to model that data statistically or physically to understand and interpret the results. And then you'll have a question of how certain are you about that measurement, right? There's a question of uncertainty and error. And we care about those things a lot too. Right? So this class is about prediction. Right? That's why we're going to learn thermodynamics and equilibrium and kinetics, because that's the prediction, that's the theory part. Certainly in the second semester, we're going to build molecules from the ground up. That's real prediction. But we're also going to talk about how can we answer these questions, right? Why and how? What are some techniques, some methodology, different approaches that chemists have to answering these questions? And what can we learn about chemistry in this way? And then finally, it's a matter of practice or practicality. We come up with a hypothesis, we have to prove it. So we'll talk about that too, about measurement. How do you measure certain quantities? And what we're going to find, we're going to learn about different types of things that you can measure in this class. Some of them are harder than others. Sometimes we'll need to measure things indirectly. Okay? We're going to talk a lot about energy in this class in particular. We'll start about energy on Wednesday. The problem is it's really hard to measure energy. Really, really hard, just raw energy. What's the energy of this mixture? You can't do it. It's almost impossible to do that. Even though it's a real thing, energy is a real thing. To ask the question, how much energy does this system have is a very, very hard question to answer. Very, very, very hard question to answer. And so we're going to have to come up with ways to measure the energy of a system or changes of energy in a system indirectly, using variables and quantities that are easier to measure. Okay? Part of that is spectroscopy. That's why we use spectroscopy, is it's a way for us to measure energy indirectly. Okay? So the class is focused on these three things. And what we're going to do starting on Wednesday, we're done now, is focus on our first major thing that we need to measure, which is energy. Okay, so we'll start that on Wednesday, guys. So read that little article. I'm not going to quiz you on it or anything. It's just really for your intellectual stimulation. It will help motivate the discussion we will have on Wednesday about energy. We'll learn about a famous female physicist who is somewhat unappreciated, and her connection to energy on Wednesday. You guys have a good one.
You made it entrance. That felt like an entrance. I was lost. I saw that. Actually, were you like, okay? I want to make sure.
No, oh, I forgot about labs. No, they start on the 9th or the 10th. We'll talk about them on Wednesday.
Okay.
2 weeks from now.
Thank you.
You're welcome.
I mean, I had this, like, I probably would. I was
Quick question on the syllabus.
Yes, ma'am.
Is there,
I'm sorry. I know.
you're good. It happens, I understand. Canvas sometimes does that.
Yes.
For the syllabus, for the chapters in the book, is it chapter 25 that's for the next one? Or is it just like,
yes.
okay.
Because this book starts in PChem 2 first.
Okay.
So the second semester is the first chapters, and the first semester is the
Okay,
chapters.
because I have a PDF version of it. I just wanted to make sure it was like
Yeah, so the first chapter you should look at, let me just double check.
It is 25.
I think it is I'm pretty sure it's 25.
Yeah, that's what it said. I just wanted to make sure that it
No,
wasn't.
it's not 25. I gotta change that.
Okay, cool.
The first chapter you should look at would be chapter 16 and math and math chapter H.
Okay.
Yeah.
I was just curious.
Hi. I just forgot to mention before that I prefer to be called Joe instead of Joseph.
Joe.
Yeah.
Okay.
Thank you.
Thank you. What's up, man?
So you teach both lab sections too, right?
I teach one of them.
Do you teach tomorrow at 8 a.m.?
That's who I am.
Is that
No,
your section?
I teach Monday nights.
Okay. Okay.
Shut up.
So, but do we have lab this week at all?
It's
No,
so
I forgot
funny.
to mention it. Labs don't start
Greg, you
till
made a
the
mistake.
10th. So 2 weeks from now.
Oh wow,
Yeah,
yeah, because
yeah.
next week we have
You don't
Labor
say
Day.
you
That's
are
right.
going to.
That's right.
Okay.
So 2 more weeks.
Start something.
I'll make an announcement about all that. And I'll talk about it Wednesday. Thank you.
Thank you. Have a good one.
You too.